Okay, so the next talk is by Professor Anthony Weaver, and he's going to talk about Ravi's work on discontinuous groups. Yeah, go ahead.
Okay, well, thank you very much. As I said to Ravi, I'm sorry that I couldn't actually be there, but this miracle of technology is making things, pretty possible anyway. So, I wish I could have seen more of the talks, and I hope that what I'm going to say isn't going to be too redundant. I really just, when I thought about this, I thought, well, let me just go back and look at all of Ravi's papers that I've read. So I got out my file, my K file, and pulled out, about 15 papers or so that I had read over the last 30 years or so. And, it was a real pleasure to go back and read through those papers and remember how much I had learned from Ravi and how many things I learned that I forgot that I learned from Ravi. And they just sort of became part of my mental equipment. But so then I just thought, well, I'm sure I haven't read all of Ravi's papers, but I have read most of them, I think, that have to do with a broad subject of discontinuous group actions on topological spaces. Just a little bit of personal introduction. I read about Ravi and was intrigued by him before I actually met him. I was in 1993, I was a second-year graduate student. At that time, I was interested in general relativity, or at least the pseudo-Riemannian geometry behind it. And in Del Carmo's great book on Riemannian geometry, there's a point where he states what he calls a remarkable fact that Gauss's theorem egregium, which is essentially that metric determines curvature, has a kind of converse in dimension greater than or equal to 4. It's definitely false in dimensions 2 and 3. The statement being essentially a diffeomorphism that preserves curvature is an isometry if the dimension of the manifold is 4 or more. And the reference was to Ravi Kulkarni's Curvature and Metric in the Annals of Math from 1970, which must have been very close to Ravi's first paper, I think. But he'll correct me if I'm wrong. The title alone impressed me. That curvature and metric. And then I spotted at the graduate center where I was going as a second-year graduate student that he was in fact teaching a course called Topics in Discontinuous Groups. I believe it was spring of 93, it might have been 94, I'm not sure. Of course, I knew that space forms were quotients of complete Riemannian manifolds of constant curvature by groups of isometries acting discontinuously. So I thought, well, this is a course I have to take. And that was the beginning of my relationship with Ravi. The course was fantastic. I still have my notes from it. When it came time to start looking for a thesis advisor, I had an opportunity to work with someone who had a lot of money and a big grant. And I turned it down because I just didn't find it as interesting as the kind of ideas that Ravi presented in his talks, his big picture context that he always put his talks and courses in. So I went to him and he floated 2 possible topics for my thesis. One was something having to do with Lie groups and Z classes, which was very intriguing. And the other was something about moduli spaces and Riemann surfaces. And I chose number 2, of course, because of my interest in surfaces and geometry and the ubiquitous name of Riemann again. So that was the beginning of starting to read some of Ravi's papers. As I say, not all of them. And I'm going to present about 10 or 11 of them in their chronological order, but of course, that's not the order that I read them in. Because whoever reads anything in chronological order when they're trying to learn something. So the first, I guess, the earliest paper, I would call it an paper, in that it was the beginning of Ravi's investigations on the very broad topic. The broadest possible context being the limit set lambda and the domain of discontinuity omega of a group gamma acting on a topological space X. Of course, the classical case here is are the discrete subgroups of Möbius transformations or Kleinian groups acting properly discontinuously on non-empty subsets of the Riemann sphere. And a subcase of that, of course, is the case of Fuchsian groups acting on the upper hemisphere, which is essentially the interior of a disk. And the quotient spaces of those actions, which are, of course, Riemann surfaces of finite type, meaning being compact with some possible boundary and having possibly finitely many punctures and cusps. Well, the crucial idea of that paper was that under very weak restrictions, each component of the boundary of the limit set contains what is called a gamma accessible point. And the consequence of that idea is that the limit set has at most two components or uncountably many components and is a perfect set. And if gamma is torsion-free, it's a free product of subgroups of one or two limit component proper subgroups. And this very broad results, these results are powerful enough to give the group theoretical structure of finitely generated Kleinian groups without using any features of complex function theory or conformal geometry. So, of course, that I think that's really remarkable in that, it gets to geometry and complex function theory from a purely group theoretical point of view. The next paper, I guess, along these lines in 1983, he has a paper called An Extension of a Theorem of Courage and Applications to Fuchsian Groups. So Courage, of course, had given the structure of a subgroup of a free product. And what Ravi did here was he extended and he specialized Courage's theorem to non-co-compact Fuchsian groups by giving necessary and sufficient conditions for the group up here on top to be a subgroup of the group down here on the bottom. The structure being, this is a free group of rank S, free producted with a free product of a finite number of finite cyclic groups. So necessary and sufficient conditions for the top group to be a subgroup of the bottom group with a given finite index D. And of course, well, here are some of the conditions. I guess I maybe don't have to go through all of them, but of course, the free rank, there's a condition on the two free ranks, and there's divisibility condition on the orders of the finite cyclic factors, and a version of the Riemann-Hurwitz relation. And then a Diophantine condition. So you look at the set of distinct cyclic periods, and you look at their multiplicities, and then you define, you sort of kill off any relationship where there's no divisibility of the appropriate type by making it 0 here and 1 here. And then what you get is this Diophantine system, which must have a solution in non-negative integers. And so this is a very difficult problem. This is a Hilbert problem. And it crops up all the time in these situations. So what Ravi did here, I think, you know, this opened up a lot of work for a lot of other people to do more work, but in general, he gave a method for finding or enumerating non-negative solutions of a general Diophantine system, right? So the AIJs, the BIs, they're all non-negative integers, and you want solutions in XJ in non-negative integers. Oops. So he gave, well, he wrote them as formal power series. I'm sorry, can you give me 1 minute? I just have to answer the phone. Hey, I'm giving a talk. I'll call you back, okay? Right, sorry about that. That was my wife. Early in the morning here. Right, so he gave these generating functions. The sigma generating function is essentially has coefficients which are the number of solutions x, where x is interpreted as the vector x1, x2, x3 for a given b, which is also interpreted vectorially. And this abstract generating function has coefficients which are the number of solutions for a given b. And turns out these are rational functions, and moreover, Ravi gave recursions for them. So really the best you can do in terms of enumerating, you can't get closed formulas for solutions of these Diophantine systems, right? So this is really the best you can do. Very elegant result. So then moving on to the early 80s. And we have Alan Edmonds here, and he was a collaborator of Ravi's when they were in Michigan, right? Is that where it was? Along with John Ewing. And they did-
Indiana.
Indiana, I'm sorry, thank you. Yeah, Indiana. So this series of papers started out with regular tessellations of surfaces and PQ2 triangle groups. And then became generalized to torsion-free subgroups of Fuchsian groups and tessellations of surfaces. And then Ravi later on extended it to normal subgroups of Fuchsian groups. The normality condition makes things a lot more complicated, brings in number theory. Anyway, just so basically a PQ pattern on a surface is a tessellation by p-sided faces, q of which meet at each vertex. And this is a classical subject. So if M is a closed surface with Euler characteristic chi of M, then if you've got positive integers p, q, v, e, f, and they satisfy the Euler characteristic definition, V for vertices, E for edges, F for faces, and these other conditions, PF2E equals 2 equals QV, then there exists a PQ pattern, and the pattern can be geometrized. In other words, the sides can be made geodesics. There are a few exceptions. There's one exception. But if M is not a sphere or a projective plane, the PQ patterns on M are classified by conjugacy classes of subgroups isomorphic to the fundamental group of the surface of the extended Schwartz triangle group of type 2PQ. So actually the triangle groups are special cases of Dyck groups, which we'll talk about in a minute. Yeah, just some comments here. There is some identification of side edge pairs that's necessary. So you have some singular faces. It can all be resolved in the universal cover, but if you want the pattern on the actual surface, you need some identifications and some singular faces. And the basic technique was lifting of patterns through cyclic branched coverings. And again, this does have a long history, all the way back to Frick and Klein, Hurwitz, Burnside, and sort of misting off into folklore, going way back, even as far as Kepler. A notable group theoretical consequence here is that the indices of torsion-free subgroups in PQ2 triangle groups are precisely 2kn, where n is the least common multiple of the periods 2pq. So generalizing this all to torsion-free subgroups of standard Fuchsian group. So the standard Fuchsian group with all the bells and whistles has these 2G hyperbolic generators, R elliptic generators, and S parabolic generators, satisfying this long relation here, product of commutators and product of everything equals 1. And the X's are of finite order, M1 through MR. And for it to be Fuchsian, the characteristic of the group, which is this integer, must be positive. Otherwise, it acts on a hyperbolic surface. If it's 0 or negative, then it acts on the sphere or the torus. So the theorem in this theorem is that G has a torsion-free subgroup of finite index K if and only if K is divisible by either the LCM of all the finite periods or twice the LCM of all the periods. And whether it's twice or 1 depends on whether G has what's called even type or odd type. The odd type definition is that there are no cusps. S is 0, no parabolic elements, and lambda, the LCM of the periods, is even, but the number of odd quotients is odd. So in terms of the proof here, the necessity of the conditions and the sufficiency when the genus is positive and when there are cusps is fairly easy to prove. So the bulk of the paper deals with the abstract group where S is 0 and G is 0, right? So there are, none of these guys are here, and none of the Y's are here. So it's just an abstract Dyck group. It's got R generators. Their product is 1, and each one is of finite order. It's convenient in the proof to include cases which are not Fuchsian. The Fuchsian condition is simply that this sum be non-negative. But it's also convenient to consider some degenerate cases where some of the mi's are equal to 1. In other words, some of the x's are identity elements. Then the definition given is that a type is allowable if at least 2 of the entries are greater than 1. And if only 2 entries are greater than 1, they must be equal. And then a Dyck group of allowable type is realizable as a group of isometries of a space form, space of constant curvature, having curvature -1, 0, or 1, depending on whether this sum is respectively positive, 0, or negative. So allowable types are realizable as groups of isometries of space forms. So you can realize these groups of isometries geometrically by taking a polygon in the space, covering space, H, which is usually hyperbolic space, with R geodesic sides and interior angles determined by the periods of the group. And then the Dyck group is the orientation preserving subgroup of the group you get by just looking at all the reflections in all the sides of this polygon. But you take the orientation preserving subgroup of that. So a fundamental domain is sort of two polygons stuck together, right? P together with a reflection through one of its sides. The cases where R equals 3, of course, are the triangle groups that they treated in the previous paper. Well, some more generally, right? They treated 2 PQ cases, but we're talking general triangle groups here. So the image of P, if you take that image under the group, the full group, you get a standard geometric tessellation of the type M1 through MR. And so this is sort of the generalized theorem from the previous paper, right? If you got an closed orientable surface, you've got a bunch of positive integers satisfying the Euler characteristic condition and some other arithmetic conditions. Then there is a tessellation of the surface into a certain number of argons with a certain number of edges and vertices of appropriate valences related to the periods. Yeah, here they are, 2M1, 2M2, 2M1. Right. Yeah, so there is a purely group theoretical consequence here about existence of permutation groups with prescribed cycle structures. So if all those conditions hold, right, then essentially you can get a group generated in the symmetric group on n symbols, where n is related to the LCM of all the m's, the mi's, where each of these R cycles is the product of n over mi disjoint cycles. The product of all the cycles is 1, and they generate a transitive group of permutations. And so that was a purely group theoretical or permutation theoretic question that was, that is nicely answered here by this construction. And the proof is actually quite elegant. It's just, you just look at the coset permutation representation of the Dyck group. Modulo a torsion-free subgroup of index n. All right. So yeah, now let me move on to when you throw in the condition that you want normal subgroups of Fuchsian groups, in particular, torsion-free normal subgroups of Fuchsian groups, then you're really constructing Riemann surfaces, compact Riemann surfaces. If you have torsion-free normal subgroup of minimal index in a PQR triangle group, where PQ and R are primes, then of course the quotient groups must be finite simple groups, because they're quotients by normal subgroups of minimal index. There are no other smaller ones. So this is Ravi's paper, and he has what I guess I would call it a pseudo theorem. Almost always, these quotients here of PQR triangle groups are PSL2 groups over a finite field with S elements. It's only pseudo in the sense that it depends on the Riemann hypothesis being true. So it's well, depending on your religion, it's probably true. Anyway, it's certainly in all cases looked at seems to be true. There are a few exceptional cases which Ravi talks about, the alternating group of degree 7, the small Janko group, a certain PSL3, which occurs once as the minimum quotient. But in this paper, the geometric techniques like tessellations are much less effective. And what, as I said before, what plays a much deeper role is number theory. And there's a dependence on the completeness of the classification of the finite simple groups, which I guess was less certain in 1985 than it is now. And I guess it's certain now, but I'm not sure. So let's see. Yeah, so then he also just treated some general cases, just finite quotients of arbitrary finitely generated Fuchsian groups, solvable quotients, which were so not necessarily minimal, but quite small in relation to other quotients that had been found and were in the literature before this paper. Once again, the important case being the Dyck groups. The theorem being there that a Dyck group does contain a torsion-free normal subgroup of finite index. A crucial group theoretical result is that if a Dyck group has a normal subgroup of finite index, there's a torsion-free normal subgroup of which phi is a pullback by a surjective homomorphism. So that is a useful technique, a useful fact to have at hand. So some of the results here is that are these, and I'm only quoting a few of them. So PQR, where they're distinct primes, there are no solvable quotients. If you have a Dyck triangle group of the type PQQR, there is a two-step solvable quotient, but not a one-step solvable quotient.
Classification is for torsion-free or general case?
Well, torsion-free, because we're talking about solvable quotients. Yeah, I mean, I guess I'd have to go back and check, but I think we're talking torsion-free. I'm not sure right at the moment. I don't know if Ravi remembers that far back.
Mostly torsion-free, surely.
Yeah, I believe so. Anyway, you can look up the paper. It's a great paper. But then, you know, all sorts of results like this are very useful, and they open up a lot of areas of research which many people have taken up in the years since. So when are there nilpotent quotients? When do you have nilpotent group actions, but no abelian actions? Here's a particular example where there's an abelian quotient, but no cyclic quotient. And then, of course, that's on a specific genus.
Some references for further study on these things?
I'm sorry?
Some references on further studies on these classifications?
Oh, there's many further studies. Yeah, I mean, as I say, I'm just going through Ravi's papers and sort of trying to quickly summarize the things that he did. And as I say, he opened up massive avenues where people took them up, and there's been a lot of work since. Anyway, I would like to, so this paper in 1987 called Symmetries of Surfaces, I mean, this is my personal favorite because it's so groundbreaking. It just opened up a whole nother point of view here. And it's one that I used a lot. And I think this paper must be cited it must be among the most cited of Ravi's papers, at least in the field of groups acting on surfaces. But the change in perspective here is that you fix a finite group and you look at the set of genera on which that group acts as a group of orientation preserving homeomorphisms of some compact orientable surface. And, by Hurwitz's theory, this all becomes complex. These become Riemann surfaces with complex structures, and hyperbolic metrics. But of course, the general case is purely topological. And one of Ravi's themes was always to boil it down to the purely topological essence, which he does later on in some other papers. But anyway, the main idea here is that if you sort of divide groups into two types, which I'll talk about later, then there exists a positive integer, which depends only on the cyclic P deficiencies of G, which I'll define in a second. But what it says is G acts on G. If G acts in genus G, then G must be congruent to 1 mod this integer or twice this integer. And conversely, for any G congruent to 1 mod this integer or possibly twice this integer, G will act on a surface of genus little g, except for finitely many exceptional values. So this opens up the idea of the genus spectrum of a group. And I know people attending this conference have done a lot of work on this. I've done some work myself. So every group has a genus spectrum, right? The set of G's congruent in the appropriate congruence class for which the group acts in that genus, and the finite gap sequence, the set of G's in that class where it doesn't act. And of course, of interest is the last gap, right? Which is called the minimum stable reduced genus. You have to reduce modulo the integer n or 2n, of course. And then you know that everything beyond that in the appropriate class has a surface admitting the group action. And again, the enumeration of the genus spectrum in general is a very hard Diophantine problem. Right, so just some quick definitions. So if P divides the order of a group, finite group, then the cyclic deficiency of the group, the cyclic P deficiency, is the px, well, the order of the group minus the exponent, right? So if they're equal, then it's a cyclic group, right? Otherwise, it's less than cyclic. So the P exponent, right? EP is the P exponent. It's the smallest power of P such that every element is the identity to that power. So Ravi defines this thing, which is almost the cyclic deficiency, except in a couple of cases. It's the cyclic deficiency if P is odd or P is 2 and the 2 group is actually cyclic. And otherwise, it's 1 less than the deficiency. And this gives a formula for the n, which is almost the stable genus increment. Whether it's n or 2n depends on, as I said, whether it's a type 1 or type 2 group. And it takes a while to get your head around these definitions, but these are the definitions. A group is of type 2 if the elements of non-maximal order don't form a subgroup. So if you have a homomorphism onto Z2, the preimage of the identity are the elements of maximal order, but the preimage of the non-identity, so therefore not a subgroup, are all the elements of order of non-maximal order. Otherwise, it's of type 1. And so the stable genus increment is then determined by the type of the group. So many applications of these results. One question is which groups act in all but finitely many genera, which means that the stable genus increment must be 1, right? So that yeah, there's a gap, which is really a gap sequence, and then everything beyond the last gap, every genus admits a group action. Well, those groups are precisely the cyclic groups if P is odd. And if it's a 2 group, well, if it's a group, yeah, its CeLO 2 subgroup must be cyclic, dihedral, generalized quaternion, or semi-dihedral, just those 4 types. Another interesting result is if it's a simple group acting in even genera, then it's basically always, almost always PSL2 FQ, sometimes PSL3, sometimes PSU3s, and a couple of exceptions. Other applications are, there are very tight order bounds for P groups acting in genus G, and these are bounds analogous to Hurwitz's general 84G-1 bound that are also very useful if you're looking for the groups acting in certain genera. I see that I'm running a little short on time, but I just want to jump ahead to some papers, all of which essentially, they all came out in 1991. And one of them with McLaughlin was a real close analysis of cyclic P groups of symmetries of surfaces, including the gap sequence and closed formula for the gap sequence, the stable genus. And this work has been picked up. I know Siddhartha Sarkar has worked a lot on P groups of symmetries and the genus spectrum since then. These 2 papers in the Finnish journal, isolated points in the branch locus and a note on Wiman and Akala-McLaughlin surfaces, they appeared one after another in the same issue of the journal. And again, it's a sort of change of perspective. And then there's this 4th paper on infinite families. But let me just say, I guess here's what I was talking about, Ravi boiling things down to their topological essence. I believe he was the first one to point out that this theorem of Carrick-Yarto, which I hope I'm pronouncing correctly, that essentially any orientation finite cyclic action on a disk is equivalent topologically to the standard action, which is rotation around the origin by integral submultiple of 2 pi. So if G acts on a compact orientable surface with a fixed point, then G is finite cyclic, and there is a polygon with a certain number of sides and a side pairing such that the polygon modulo the side pairing is homeomorphic to the surface, and the G action can be modeled, and Ravi really simplified these models of cyclic actions in a canonical way by defining a certain action on the polygon, commuting with the side pairing, and such that paired sides are not in the same G orbit. And showed that conversely, if you've got any polygon with a side pairing and a cyclic action, which commutes with the side pairing and separates the paired sides into distinct orbits, then it induces a cyclic action. I guess the main example that he started with is what would be a natural base point in the moduli space of compact Riemann surfaces of genus G. greater than 1, the Wiman curve. This is the curve, the unique surface that has a cyclic automorphism of maximum order 4G plus 2 in every genus. And moreover, that's the full automorphism group of the surface. It's covered by this particular triangle group with 2G plus 1, 4G plus 2. So therefore, there is a torsion-free normal subgroup of the appropriate index in that Dyck triangle group. Anyway, so yeah, I mean, I guess in the interest of time, I won't go through every detail here. But this is really the construction of the hyperbolic polygon in the universal cover, which models this action. It's got 8G plus 4 sides, and sigma is the side pairing, right? And you can see that, so you have to label the vertices in a cyclic order. The side pairing pairs an odd vertex with an even vertex. And so the cyclic action is then this product of two 4G plus 2 cycles. So it is a 4G plus 2 cyclic action. And it's clear that the side pairing separates the orbits, right? So there's always a vertex from the odd orbit paired with a vertex from the even orbit. Right, so these are beautiful models to construct and play around with. And Ravi did them for several families of classical curves, the Akala-McLaughlin curve, another Wiman curve, Klein's quartic. Akala-McLaughlin curve is it's the minimum maximum order of a group acting on a surface of genus G, 8G plus 8. There are infinitely many genera in which that is the maximum order automorphism group. And it's a specific surface. Anyway, I won't say much more about that. Yeah, just to say a little bit more about the branch locus. So if you have to restrict to genera greater than 2, then the branch locus is just all the surfaces that admit some non-trivial automorphism group. And this locus is a quasi-projective algebraic variety. And the subvarieties correspond to topological types of group actions. And they have a very complicated nesting structure, one variety and another, depending, of course, on how one group sits inside another. But one of Ravi's papers, which was really groundbreaking, I think, was the idea of, are there any isolated points, right? So connected subvarieties of dimension 0, so essentially points or sets of points that do not sit in any proper subvariety of higher dimension. So it turns out that, well, if it's isolated, its automorphism group, well, they have to act basically with a triangular action. And in fact, it has to be a cyclic prime order action where the prime is actually twice the genus plus 1. The work here depends a lot on looking at finite index inclusions between triangle groups. Work of David Singerman is important here. Quickly, I know I'm running out of time, so please tell me if I need to shut up. I think I'm almost finished. I have a few more slides. But anyway, so he brought into this notion of the characteristic symbol of a ZQ action. The data is QQQ, and the symbol really determines the rotation angles at each fixed point. And the rotation angles really are defined up to equivalence. There's an action of ZQ star, right? The non-zero, the multiplicative group of order Q, essentially meaning that you can take R to be 1 in any triple, right? You can always normalize it in that way. So here are some quick results. So if you have an isolated point, no two of those rotation angles can be equal. If the prime Q is congruent to 1 mod 3, the Nielsen signature can't be 1 lambda lambda squared, where lambda is a cube root of unity. The number of isolated points, genus greater than 2, is the floor of G minus 2 over 3. If 2G plus 1 is prime, of course, and not 7, and 0 otherwise. The exceptions are really interesting here. The case where 2G plus 1 is 7 happens in genus 3, of course. The characteristic symbols are 115 and 124, and those are precisely the Wiman curve of type 1, which is hyperelliptic. So there is a Z2 variety on which this sits, so it can't be an isolated point. And the other signature is 124, which is the Klein quartic. And of course, that has PSL Z7 acting on it. So there are lots of subgroup varieties on which that point in the moduli space sits. So obviously that's not isolated. Just one remark, if you want to include genus 2, then you have to make a different definition of isolated, because every surface is hyperelliptic. So if you mod out the hyperelliptic involution, then the Wiman curve of type 1 could be considered an isolated point. Right, this was a late paper, which is great to read because it kind of summarizes a lot of his previous work. It was actually a preprint for 6 years. It's really contemporaneous with the previous 4 papers. So it has I highly recommend it. It was out and cited in the other papers, but never actually was published until 97. Just very, very briefly, summarizing some of the results. If you put order bounds on the order of the group in terms of the genus, you get some very, very precise results about what groups act and with what signature. So a large group is defined as greater than 4G minus 1 in order. If it's large and cyclic, then it must be the Wiman curve. Or the Wiman curve, a different closely related Wiman curve. Or it belongs to a 1 complex dimensional subvariety in the genus 2 moduli space acting with this branch data. So it's 1-dimensional because it has 4 branch points. Or it's one of 6 exceptional curves in genus 2 through 6. So that's it for me. Ravi, I just want to wish you a happy 80th birthday. You were the one who told me when my father turned 80 that, oh, that's 1,000 moons. And indeed it is, or very close to it. If every year has 12 full moons, then it's a little less. And if it has 13, it's a little more. So anyway, many more moons to come. And Ravi, I'm very grateful to having met you and worked with you over the years. Thank you all.
Thank you, Professor Weaver.
Perhaps I should unshare my screen now. Yeah.
Anyone has quick questions? Yeah, go ahead.
Yeah. Hi, Tony.
Hey, Siddhartha.
This is Siddharth.
Yeah, how are you?
there is a problem of voice probably. Can you see me? And
Yeah.
yeah, okay. So I was about to ask a couple of questions. So first of all, is there any systematic study of from the action or the data, what could be the dimension of the certain isolated points? Let's say if you look at the Teichmuller space, what are the marked surfaces and what could be their dimensions as a subvariety? So for example, hyperelliptic involutions. So there is a one-dimensional one parameter family.
Well, no, the hyperelliptic subvariety is very high dimensional, right? It's
Okay, sorry.
2G plus 2.
Yeah.
Yeah, I believe.
So is there some kind of formulae or some kind of theorems which actually you can employ there?
Well, again, I mean, you talk about dimension of isolated point, dimension is 0.
Yeah.
So it's really just a single surface.
Yeah, but how do I decode it from the data?
Yeah, well, I mean, that's a long, I sort of ought to defer to Ravi here sometime. But maybe we can talk offline or something, or in a different venue.
Sure.
Because I think it's a long story, really.
Yeah, sure. And I have another question which was related to this Diophantine equation. So for example, before you just begin with the study, so this basically, you pose it as a Diophantine equation, and I think prior to this, there are a lot of works. Even Ardos has a work, which was like 3 coefficient, 3 variables, and whenever this smallest possible solution perhaps exists. Is there any closed formula or something? So there are some kind of estimates now. But is there a way to kind of tell that, okay, so this is not arbitrary coefficients. So these coefficients actually come from the group action on Riemann surfaces. As you look forward to this Euler characteristic equation, and then you tailor-made these coefficients. So it looks very special to me because in a sense, whenever I try to experiment with a very exceptional group like sporadics of very high orders, then also it looks like there is a kind of reductive pattern, and probably this is solvable always. So although in general I cannot say there is a closed formula of smallest such equation, but for groups acting on data coming from the group actions, probably there is a closed formula.
I think in general, non-negative solutions of Diophantine systems are not solved. This is Hilbert's something problem, right, Ravi?
Yeah.
Which is why it's difficult. I mean, of course, special cases. Yeah, I mean, it's possible to get some results, but it's very hard. I mean, I know you've done a lot of work on this, and I have too. But closed formulas and general results, very difficult.
If you look at this, even the cyclic groups of order PQ case, I mean, was there some immediate thought about whether I can just look at the minimum smallest?
Well, I have a paper on that actually.
Yeah.
I haven't solved it. It's very difficult. ZPQ? Yeah. It's the tough Frobenius problem.
Okay. Yeah. We'll talk about that.
Yep.
Sure.
Is it dinner time now?
Hello. Hello.
Yeah, Ravi wants to ask you some questions.
Did you?
I didn't hear that, if that was directed to me.
Subgroups are the arithmetic geometric method in the study of the subgroups of the modular group. Did you read that paper?
I will then. You have to send it to me. I'm hearing an echo here, so I'm not quite here. No, I don't believe I read that. I told you I haven't read all your papers.
No, there was more number theory there. This is fairy symbols paper.
Okay. Sounds good.
Okay, so let's thank Tony for his nice talk. Thank you.